I will talk about understanding the mechanisms of circulatory effect at low doses. Oh, this is not functioning. Okay. Yeah, so this shows you the vasculature. Can you actually take this in your hand? Without breaking it. So this shows you the vasculature, and here we very nicely see also the heart vasculature with the coronaries and with the microvasculature. And all vasculature has this kind of a structure. So the inner layer is the endothelial cell layer in the intima. Then we have the smooth muscle cell layer in the media and fibroblasts in the adventitia. And this also shows you endothelial cell layer here quite nicely. So it's more rough than here. Here you see the red blood cells. So what is the function of the endothelium? It is a barrier between the blood and the tissue underneath. It needs to keep the vascular tone. That means vasoconstriction and vasodilation. And here the nitric oxide is very important for this function. So it has to be on a certain level. It's also important for the thrombosis and fibrinolysis of blood clotting, and it responds to inflammation. So it can produce cytokines and chemokines. It produces adhesion molecules, but there are, of course, other cells as well that can produce cytokines and chemokines, and to a more extent than endothelial cells. So I want to just show you how the adhesion and migration happens, because this is the first step of acute inflammation, but this is also the first step of atherosclerosis, so it's very important for both. So here you have leukocytes. If you have some inflammation in your body, so they need to get to that place. So they need to transmigrate the endothelial cell layer. So endothelial cells, they start to express selectins and later adhesion molecules, ICAMs, VCAMs, PCAMs. And the leukocytes, they are rolling on the endothelial cell layer, they adhere, and then they transmigrate. It's the similar process in the atherosclerosis, which is also kind of inflammation. So here you have in the normal cells, you have the endothelial cell layer is nice and as a monolayer here. If you have atherosclerosis, you have the same procedure. So endothelial cells become adhesive, and they let through T cells, macrophages, those form foam cells, and finally push up the smooth muscle cell layer and form a plaque, which can then rupture. And this is associated with increased ROSC, increased oxidative LDL, a decreased nitric oxide, calcification, and fibrosis. So when we talk about radiation-induced heart disease, there are two main things that we see. It is in the coronary arteries. The atherosclerosis is one increased factor, but it's also in the heart tissue, in the microvasculature, the microvascular insufficiency. I will not talk about the fibrosis because it's a different story here. We also have other symptoms like acute and chronic pericarditis and injury, valvular injury, and injury in the conduction system. But I'm not going into that. So I start first to talk about a little bit the high dose response, so that you know what we would like to see with the low dose. So this is an old experiment. In those days we didn't have the Sharp machine, so now we have it. So we just irradiate the mice locally, but they were covered with shielded with lead. Sorry, and even though only the heart was actually irradiated, there's always a piece of lung, even with the SARP, that gets irradiated. But here we have a much bigger scatter dose than with the SARP, which has practically none. So then we isolated the endothelial cells after 16 weeks using magnetic beads. And when we took out endothelial cells from these hearts, we saw that ICAM1 and ICAM2 are increased if you have these irradiated conditions here. So it means that even in vivo, the adhesion molecules are increased after irradiation. Or actually, this was measured ex vivo, but they come from the body of the mouse. So when we further studied what are the pathways that are activated here, so this was the main pathway, and this is the insulin receptor PI3K AKT eNOS pathway. And all these steps were blocked. So meaning at the end you have more active endothelial nitric oxide synthase. And this we also then measured in the serum of these mice, so we could see the nitric oxide with these 2 doses of 8 and 16 gray. It was downregulated. It was less of it there. And as I said, NO is very important for the heart, for the proper functioning of vasodilation, vasoconstriction. Also, we saw in the serum an increased oxidized LDL, only in the irradiated ones. We saw increased pro-inflammatory cytokines like IL-1 alpha, IL-6, TNF alpha. So it is a systemic effect now coming from a local irradiated heart. We could also say that in the heart muscle, the proteins, or this is actually in the endothelial proteins, we could see a lot of different modifications like nitrosylation, malondialdehyde modification, homocysteinylation, carbonylation, and all these proteins, they are not functional. We also saw decrease in the SOD1, for example, increase in the HSPs. So we could say we have an increased oxidative stress after radiation in the endothelium. We also saw increase in the P16 and P21, and these are senescence markers. So we have increased expression of senescence markers after irradiation. And this was not so long time after irradiation. This was 16 weeks, but we could not go further. We have shown that if you go further, then you see this much more even, this senescence. So now I will go to the low dose, and I will talk a lot about the pro-cardio effect that we did. So here we used human coronary artery endothelial cell line, and this first experiment is measuring adhesion. Here, so this is work done by Claudia Fournier from GSI. Here you see the doses. I hope you can see the doses. So the first one is 100 milligray, 0.5, and this is 2 gray. So even all these curves, even here we are looking at the IL-6 expression, IL-8, MCP1 that attracts monocytes. You always see a similar kind of a curvature here, so maybe it goes a bit down and then goes up. But this one, these points are not significant. The only significance that we get is here, because there's a quite big error bars here. So we see a significant IL-6 increase with the 2 gray dose. And we did not see any significance with the lower doses here. So we published the 2 gray dose. So in this paper by Björn Baselet, might know how to say the name. And we saw there that with 2 gray you have increased adhesion and release of pro-inflammatory cytokines. we saw no effect at low doses, no significant effect. We only saw these trends, yeah. With iron ions, we saw actually decreased adhesion, but increased release of pro-inflammatory cytokines and at high doses. This was another work package in ProCardio. This was led by Ken Raj from FEE. And he used a very nice 3D co-culture system with endothelial cell layer here, and here you have smooth muscle cells. So he was measuring the LDL insudation assay, because also the LDL is going through the endothelial cell layer if it is irradiated, or if it's irradiated. We know that from the higher doses. And he also measured the monocyte infiltration. This is the LDL uptake post-irradiation. So he measured, this is the control, 50 milligray, 100 milligray, 500, 2 gray, and 10 gray on day 1, 4, or 7. And to put the long story short, the only significant points were the 2 gray at 7 days and the 10 gray at 7 days. So even you see a tendency here at 0.5, it doesn't, this is only one measurement, but when he did 3 or more times, you didn't get the significance there. This is the adhesion of monocytes. So there is, you can see here as well, there is a nice dose-dependent increase on day 7. So this is days 4, 7, 12, 17, and these are different doses, 0, 50 milligray, 100, and 2 gray. This was the only point that was actually significant with 1 star. It is the 7-day 2 gray point, and all the others were not. So what he actually finally published was the 10 gray dose, where he could show that after 10 gray, these cells become senescent if you wait long enough. And this is the beta-galactosidase. It goes up quite nicely with the time. So the last time point is 3 weeks. And similarly, the monocyte adhesion goes up with the time. So at 3 weeks is at highest, and he could also show that the monocytes adheres exactly to those cells that are senescent, and make clusters like this. Yeah, then we wanted to look at the effect of dose rate. So we did some cooperation with the Japanese here, with the Rokasho. We had a female C57 Black 6 ApoE knockout mouse, and we had chronic gamma rays exposure at low dose rates, so 1 milligray per day or 20 milligray per day. And after that, we immediately sacrificed the mice. And yeah, this was done this was under the leading of Ignacia Praga-Tanaka in Rokasho. So we started irradiating these mice when they were 60 days old, and we looked either 15 days or 300 days afterwards. We had cumulative doses of 0.3 or 6 gray. And Maria Teresa is sitting in the audience, so all questions concerning this you address to her. So she measured, because that's why we used ApoE knockout, because they form plaques. And then Maria Teresa and the group at the ENEA, they measured the plaques. So we also gave only acute dose of 0.3 or 6 gray, just a comparison. And you can see here that the 0.3 gray after 300 days, actually increases the plaque size, but it does not increase the plaque number. The 6-gray does both. In the chronic case, we have no effect on the plaque size. There is a decrease in the plaque number with both doses. The 6-gray does increase the plaque size and decreases the plaque number. And also what was seen is that the size of the plaques was different. So if you have the chronic irradiation, you see most plaques here in the Arctic arch, as seen here. If you have chronic, you have them both here in the Arctic arch and in the descending thoracic aorta. So the location is different. And this was published also. My group, we were more interested in post-translational modifications after the irradiation. So we could show that if you have 0.5 gray gamma source on these human coronary artery endothelial cells, then you have changes in the acetylome of these endothelial proteins. So they get more acetylated. And we also measured all sirtuins or all HADACs. And we could show that the most effective pathway was the RHO-A. It was activated, and we also showed this with an activation assay. So this is after 24 hours, it's activated with the 0.5. We continued with this, and so RHO-A is a very, RHO-A activation means actually that the endothelial cells don't feel good, so this is why it's so important. We continued with this in a bit different system. We had here monolayers of same cells. We irradiated with 0.5 gray X-ray here, and then we looked what happens. So also here we could see a permanent downregulation of endothelial nitric oxide synthase. So now we go up to 14 days. And we could also see now in the cell medium that the NO was decreasing. I mean, I'm sorry, you cannot see the text. This is the NO decrease. This is 1 day, 7 days, 14 days, so it is decreased. You just have to believe me. And this is RHO-GDI. It is decreasing at least 7 days. So this means RHO-A activation, and we actually measured the RHO-A activation with an activity assay, and it was increased 14 days. This is the phospho-enos to total enos, and that definitely goes down, and even at 14 days is down. This is the ROS system, so this is glutathione transferase, one of them. It also goes down, and this is the carbonyl content. So these are the oxidized proteins, the ROS response. Proteins are oxidized, the ROS response goes down. 14 days, at least 14 days. So we wanted to see why is this? Why do we have so many oxidized proteins that don't work? We measured the proteasome activity. It also went down within these 14 days. It's a quite low dose, so we were quite excited about this. We also could see an increase of the polyubiquitinated proteins. So if the proteasome is not working, then you have polyubiquitination of proteins. And these proteins are, of course, also not functional, but furthermore, they are not degraded. This was interesting. Also, we could see an increase in the senescence markers with this low dose, actually, not so low, but quite low. As you can see here, 14 days at least. We also did some work with endothelial cell lines in the cardio risk project. This was the project before ProCardio. And we used another cell line, EAHY926. I think Franz Rödel is going to talk a little bit more about this cell line. It's a human cell line. And this is an old paper we published 2011. And we could see that even with 200 milligray, we did this still on those days on 2D gels, the proteomics, and we saw a lot of spots, but we could not identify them. We identified 15, and that were significantly differentially expressed. And we looked at 2 dose rates, and we could say that the higher dose rate induced more changes in the protein expression than the lower dose rate. And we could also see that we could see more after 4 hours than 24 hours. And this, to me, would mean, okay, this effect is disappearing after 24 hours. So there is an effect with 2.2 gray, but this effect is disappearing. And also we see there now the Rho pathway activation, but it's only transient. It doesn't stay. This is not from ProCardio or CardioRisk. This is a paper that I just happened to see. So these were HUVECs. This is a primary human endothelial cell line. It's not heart specific, but it's a lot used. And this was irradiated with 0.125, 0.25, or 0.5 gray, or 2 times 0.125, or 2 times 250 milligray. And there was always 24 hours between the fractions. And I don't know if you can see this either. But this shows you the ROS formation. And actually what was, to me, was amazing was here that it is not the cumulative dose. So this is the control. The first one is the 125 milligray, and this is the 2 times 125 milligray. And this is the 250, and this is 2 times 250. There is no difference in the ROS formation. It's not the cumulative dose, it's the fraction dose here that matters. This is 0.5. And they could see that at the 45 minutes, the ROS formation was at highest. It's almost the same with ICAM1 expression. It's 18 hours after irradiation. So there is a slight increase here if you do it twice. But at the 0.5, this goes down, which is, of course, interesting. And this is the messenger level of the ICAM1. This is protein level. Adhesion is a bit similar. So here you have once, here twice. So there is an increase, but it's not double. Here also 250 and 2 times 250. This is 0.5. And I think this is very interesting. The adhesion goes down at 0.5. And I think Franz is going to talk about it more. These are not stimulated HUVECs. They also measured here the NF-kappa B expression, which is known to play a role. And also here, the increase in the NF-kappa B is not twice as big. It's almost the same if you leave a 24-hour fraction there. 0.5 again, maybe slight but not significant decrease. They also measured the gamma H2AX foci, and here also many times there's hardly any difference. For example, here after a half an hour, 250 and 2 times 250, it's almost the same. Here actually the 2 times 250 after 8 hours is lower than the once 250 milligray. So here even more so after 24 hours, this is 0.99 at 250 milligray, and after 2 times 250 milligray, it's only 0.34, and I would call this adaptive response in some sense, yeah. And yeah, this is interesting. I'm not going to talk about this because Franz is here in the audience. I just tell you that if you stimulate endothelial cells that they are in an inflammatory state, when you start irradiating them, then the story looks quite different. So we have an anti-inflammatory effect of certain doses, certain low doses. This is my last thing. Endothelial cells show bystander effect. So in this experiment, we irradiated endothelial cells with 10 gray. We let them stay 14 days, and we know that these cells now are senescent. And we take the medium, which contains the secretory associated, senescence associated secretory phenotype. And we take non-irradiated, we take that SASP from non-irradiated cells or from 10 gray irradiated cells. And we put that into non-irradiated cells. And even if the cells don't see irradiation at all, if you just expose them to the secretory, the secretome, you see that many things happen. They increase in the ICAM. So these are the irradiated cells, 0 gray, 10 gray, and these are the recipients of that secretome, 0 gray, 10 gray, always in the same order. They start increasing the expression of ICAM1, STAT1, which is also for inflammation, P38, and P21, which is a senescence marker. So this was quite exciting for us. Okay, I come to the conclusions now. So the high doses of ionizing radiation, more than 2 gray, they increase inflammation, adhesiveness, ROS production. They decrease nitric oxide and the activity of endothelial nitric oxide synthase, and they increase endothelial senescence. If we give 0.5 gray as a single dose, that increases the plaque size in the C57 Black 6 ApoE knockout mouse, given us a chronic low-dose rate irradiation, that it decreases the number of plaques. In endothelial cells, 0.5 gray activates RhoA pathway. It decreases NO and eNOS, and proteasome activity increases ubiquitination and senescence markers permanently. That is 14 days we measured. Activation RhoA pathway is seen already at 0.2 gray, but it disappears. Doses less than 0.5 gray have significant effect on adhesion in endothelial cells in short term, but not in long term. It means days. And in stimulated endothelial cells, 0.5 seems to be an anti-inflammatory, antioxidative, anti-adhesive, which Franz is going to talk about more. And also, radiation-induced endothelial senescence and inflammation may spread to neighboring endothelial cells via the secretome. So yes, this was it. If you have any questions.
Thank you, Soile, for this very nice presentation and all the data that you showed. You speak twice about induction of senescence by radiation, in vivo after high dose and in vitro after 0.5 gray. You see an increase in P16 and P21, but in general, those markers are associated with persistence of unrepaired double-strand breaks. So do you see unrepaired double-strand breaks in these systems, in these cells?
In this ex vivo experiment, it's difficult to look because we just take them out and start looking at what, yeah. We didn't measure in the cellular culture. That would have been possible. And it is possible that they are not senescence markers there, but they are something else. This is possible. We have shown previously in another paper, which I didn't go into, that if we chronically irradiate HUVECs, they get senescence, and this was shown by beta-galactosidase assay, which is still one of the good ones, and that came together with P16, P21 markers. So yeah, one should be careful. They are not only markers of senescence, they are only markers for something else. True.